Enrichment Program in Mathematics, conducted by the Department of Mathematics, Sacred Heart College for Women, Chalakudi. The aim of this program is to enhance the mathematical skills and knowledge of aspiring students. Distinguished guest, Dr. Arusha ma'am, teachers, and my dear participants, I would like to welcome you all for taking the time of your heavy schedule and making these hours with your glorious presence. Let's begin the formal session by evoking the blessings of the Lord Almighty. For the same, I invite Ms. Ruthi E.B. of 2nd PG Mathematics, Sacred Heart College for Women, Chalakudi.
ലോകം മുഴുവൻ സുഖം പകരാനായി സ്നേഹദീപമേ മിഴി തുറക്കൂ. കഥന നിവാരണ കനിവിന്നുരമേ കാട്ടിൻ നടുവിൽ വഴി തെളിക്കൂ. ലോകം മുഴുവൻ സുഖം പകരാനായി സ്നേഹദീപമേ മിഴി തുറക്കൂ. ലോകം മുഴുവൻ സുഖം പകരാനായി സ്നേഹദീപമേ മിഴി തുറക്കൂ.
Thank you, Shruti. It is a great honor to have an ardent young woman researcher, Dr. Arusha C., who is currently pursuing postdoctoral research at Tata Institute of Fundamental Research, Mumbai. Now, I would like to call upon Ms. Amala Mary Joel, the Assistant Professor, Sacred Heart College for Women, Chalakudi, to introduce the resource person of the day.
Welcome, everybody. I have great pleasure to welcome today's resource person, Dr. Arusha C. She's a postdoctoral fellow in TIFR, Mumbai, and she has learned mathematics from all over India, actually, in different parts of India, starting at PSGR Krishnamal College, Coimbatore for BSc, and MS University, Baroda for her post-graduation, and finally ISER Bhopal for her PhD. Her broad area of research is algebraic geometry, and she has been constantly encouraging students to learn mathematics, and she has been sharing the fact how to tackle and love mathematics, how she had learned to tackle mathematics from various MTTS summer camps. And I'm pretty much sure that you will be able to encourage all these mathematics lovers that are present in this program. Once again, welcoming you, ma'am, to NEPM 2021, a 10-day workshop organized by Sacred Heart College for Women, Chalakudi.
Thank you so much.
Thank you.
Thank you, Amala Miss. With great honor and respect, may I invite Dr. Arusha ma'am for taking today's session. Over to you, ma'am.
Thank you, Christina. First of all, I'd like to thank the organizers of NEPM 2021 and my good friend Lynette, who approached me for this. I was a little skeptical whether if I'll be able to find a topic suitable for this program. I hope I chose a topic which is pitched at the right level. Okay, let me start the talk. And thank you so much for organizing a program. These kind of programs are necessary to encourage and keep the spirit alive. And yeah, thank you for organizing this, and thank you for asking me to be a resource person. Okay, I'll start sharing. So is it visible? Is the screen visible?
Arusha, it is.
Yeah, okay. Good evening, everybody. Today I'm going to introduce projective spaces to you. I am not going to do anything more than probably the definition of projective space and some examples. So hence a candid introduction. And please feel free to stop me at any point of time and ask questions. And it would be great if you are able to think along with me, in the sense that just be attentive and just think why, if there are any questions. Okay, so let me start. So we'll start with an example. Yes. So imagine that you're standing on a railway track. Of course, an empty track. You can't stand there while a train is running. And okay, you can't see what I've written. Yeah. And you're looking at this unending stretch of railway tracks. So yeah, do they intersect at some point? That's the question. So when you look from here, doesn't it look like they actually intersect? So from where you're standing, doesn't it look like the gap between the tracks are getting shorter and shorter, and it might intersect somewhere far away? But we know that they don't intersect, right? Because then the trains can't be running. So this brings us to this word called perspective. What is a perspective? The dictionary definition is a particular attitude towards or a way of regarding something, or a point of view. So what we have here is a perspective. It looks like the gaps are getting shorter and it might intersect. So we know that parallel lines does not intersect in Euclidean geometry. And so that means Euclidean geometry is not enough to explain the effect of this perspective which we are seeing right now. Like these railway tracks are classical example of parallel lines. And so this concept of projective space arose in order to take into account the effect of perspective on objects. Okay. So yeah, one can take a wild guess, like which profession needed to make sense of this effect of perspective the most, right? Like what everything in mathematics came because somebody or the other needed it. So if you think a bit more, the answer would be painters and architects. So in the 17th century, Gerard Bizargus, an architect and an engineer, is considered as one of the founders of projective geometry. And it was according to him that parallel lines intersect in a point at the infinity. So so this concept that the parallel lines intersect at a point in the infinity or the horizon, this takes the idea of perspective into consideration. And taking this into consideration, this projective geometry or projective spaces were defined. And so let's get to know them. Okay. So before we get into it, let's ask this question: why we study projective spaces? So we all know that like more than 3 dimensions, it's difficult for us to visualize. So the way we understand objects in higher dimension is by considering their projections into lower dimensions. For example, if you have a building or a large area, what you have is a plan of the building or a photograph of the area. Okay. So I would say that the projective spaces are a mathematical formulation of this idea, the idea of projecting objects in higher dimension into lower dimensions. And once defined, like probably the definition might seem unnatural, but once defined, one sees that they arise very naturally. Like this is the next thing which one should define, you would feel like that. Okay, so I hope everybody is familiar with what a vector space is. At least that is what I'm going to assume throughout this talk. And to a vector space of dimension n, we associate a projective space of dimension n-1. So this kind of underlies what I was saying here, that to understand objects in higher dimension, we go to a dimension lower and see how it is. Okay. Today, I am going to define what a projective plane is. And yeah, I'll define it in two ways. One is the geometric definition, and the other one will be the algebraic definition. So the geometric definition helps us to see it, and the algebraic definitions helps us to work with it. I mean, on a pen, when you put your pen on paper, what you do is algebra. When you think what is going on, it's geometry, right? Okay. Let R3 denote the real vector space of dimension 3. I hope you all are familiar with it. And so let me recall, like R3, so a vector space satisfies all the properties of a group. It has an additive, it has a zero vector, and what else? You have the notion of a subspace, and it has a basis, yeah, and all that, yeah. Okay, right. So now let V not equal to 0 denote a non-zero vector in R3, and so you can imagine a vector in R3, right? Now let LV denote the one-dimensional subspace generated by V. I hope you all understand what do we mean by a one-dimensional subspace. It is the subspace generated by the vector. So that means LV consists of all those points of the form lambda times V. Or this one-dimensional subspace is nothing but the line passing through this vector V and the origin 0, 0, 0. So I mean, either I'll denote the origin by 0, 0, 0 or 0. It's fairly standard to do that, right? Yeah. And then the projective plane P2, we denote the projective plane by P2, and it is defined as all those lines LV. Okay, so what are we doing? We are taking a vector in R3, then we are considering the line generated by this vector LV, and then we are collecting all those lines LV and calling this P2. Okay, so now you can think of it as P2 is the set of all lines passing through the origin. A set of all lines in R3 passing through the origin. Okay. Yes. So the elements of P2 are lines through origin in R3. Okay. That R should be B2. Now, does 0 belong to P2? We started with a non-zero vector, and like 0 does not generate a one-dimensional subspace. So what is the answer? 0 is not an element of P2. Okay. No. And now let L and V be two non-zero vectors in R3. Is it possible that LV is equal to LW? I'm going to give you some 30 seconds to think about it. If it was like a Zoom session, probably there could be some reactions like yes and no. But yeah, please think with me. So you have two non-zero vectors V and W, and you have two lines LV and LW. Is it possible that these two lines are the same? The answer is yes. And the next question is, when does it happen? So if
linearly independent two sets, two vectors.
Linearly independent or dependent?
Sorry, dependent.
Yeah. Yes. You're right. I can't see your name, so yeah. Yes. Two vectors give rise to the same line if they both are linearly dependent, or if W lies on the line generated by V. Okay, that is, if W is also a vector which lies on the line generated by V, then both the vectors will give rise to the same line through the origin, right? I hope you can visualize it. So two non-zero vectors give rise to the same line through the origin if one vector lie on the line generated by the other vector. Right. Okay. Before we go into the algebraic definition, so I think the geometric definitions must be clear right by now. We are looking at a set which consists of lines passing through origin, lines in R3 passing through origin, and it is possible that two vectors give rise to the same line. We also observe that zero is not an element in P2. Okay. So before we go into the algebraic definition, let me ask you this question. Do you remember what a homogeneous linear equation in 3 variables is? I think if you think about it, you will come up with an equation of this form, right? Ax plus by plus cz equal to 0. So my next question is, why are they called homogeneous equations? Okay. And so if you observe that 1, 1, minus 1 satisfy the equation, right? Like 2 times 1 plus 3 times 1 plus 5 times minus 1 gives you 0. So 1, 1, minus 1 satisfy the equation, and so does lambda times 1, 1, minus 1 for all lambda in R. And when such property holds, that is, if V is a solution, implies lambda V is also a solution, then we call them homogeneous equations, right? So remember this term homogeneity and homogeneous equations. We'll encounter them again. Okay, so now we'll move on to the algebraic definition. So I'm defining P2 as, we already observed that 0 is not there in P2. You are removing 0 from R3. And do you understand this notation? It is R3 minus 0 quotiented by an equivalence relation. So you have this set R3 minus 0. Then on this set, you are defining an equivalence relation. How are you defining it? Two vectors, x1, y1, z1, and x2, y2, z2 are related if and only if there exists a scalar lambda in R star. R star is R minus 0, such that x2, y2, z2 is lambda times x1, y1, z1. Okay. Let me recall again. Equivalence relation means you have reflexivity. A is related to A. You have symmetric property, that is, A is related to B implies B is related to A. And we have transitivity, that is, A is related to B and B is related to C implies A is related to C. And when we have an equivalence relation, and if we consider the equivalence classes, we get disjoint classes, right? We get a nice set modulo the equivalence relation. And here the relation is two vectors are related if and only if they are a scalar multiple of each other. So if you can find a lambda such that lambda in R star such that x2, y2, z2 is lambda times x1, y1, z1. Okay. So this is the algebraic definition of this set. So how do we denote it? Like you have seen when you write quotient groups, you must be familiar by that then. Like we have a class notation. So we write P2 as square bracket x colon y colon z such that all x, y, z is not equal to 0. That is, all the three coordinates cannot be 0. And this square bracket x colon y colon z would indicate that it's an equivalence class. And these coordinates with the other, we call this homogeneous coordinates or projective coordinates. Because, in this coordinate, x, y, z is same as lambda x, lambda y, lambda z, right? Because these are equivalence classes. Okay, so this is our algebraic definition. Okay, let me summarize again. We are trying to define what a projective plane is. we had a geometric definition which said that the projective plane consists of all lines in R3 passing through origin. Now we have an algebraic definition that for that we took R3 minus 0 and defined an equivalence relation on it, and we considered only the equivalence classes. So you have an object, and I'm saying that this is also its definition, and that is also its definition. So then one has to prove that both definitions are equivalent, right? Because it's not very clear in particular that both gives rise to the same set. So yeah, and before I go ahead, now you can see why they are called homogeneous coordinates, right? Because like we saw, for a homogeneous equation, 1, 1, minus 1 satisfy that equation implies lambda 1, 1, minus 1 also satisfies. And here x, y, z and lambda x, lambda y, lambda z denotes the same point. So we call them homogeneous coordinates. Okay. Yeah. So next we move on to proving or understanding the equivalence of definitions. Okay. Because see, in one hand we had lines, and here we just have a notation x, y, z. So now we are bound to prove that both are the same, right? Okay. So how do we prove that both the definitions are equivalent? We show that both the definitions give rise to the same set, right? And to do that, we show that there is a bijective map between these sets. So what we should do is we should take a line LV and find a point XYZ corresponding to it. Similarly, we should take a point XYZ and find a line LW corresponding to it. And then we should show that this composition is identity or injective and surjective, whichever way you want to do it. Okay. Yes. So then we have to show that if LV goes to XYZ and XYZ goes to LW, then LV is LW, and the converse. That is, if XYZ goes to LV and LV goes to ABC, then XYZ is same as ABC. I hope you all are with me till this point. Yeah. Okay. Before going into a proof, let me give an example. Okay. So let's all think, what is the equation of a line in R3 passing through origin? How many data, what all data you need to write an equation of a line passing through origin? To give the equation of a line, you need a point and a direction vector. But since we know that it passes through origin, we just need another point. So we need a point on the line and a direction vector. And for example, x by 2 equal to y by 4 equal to z by 6 defines a line passing through origin and the point 2, 4, 6. If you want me to recall, the formula for line passing through a line in R3 is x minus x naught by a equal to y minus y naught by b equal to z minus z naught by c, where x naught, y naught, z naught is a point on the line and a, b, c gives the direction vector. Okay. We have this. So now we have a line. To which homogeneous coordinate will we associate this line to? Where should we send this line to, right? So we map it to the equivalence class 2, 4, 6. Okay. Conversely, a point ABC, A, B, C is mapped to the line x by a equal to y by b equal to z by c, because this will define a line passing through origin and to the point ABC. Great. Okay. So this is the example. Now we'll try to write a proof for it. Okay. So now take a line in L, take L in P2. Then by definition, L is LV for some non-zero vector V equal to ABC, right? And we sent LV to the homogeneous coordinates A, B, C. Now, the $1,000,000 question, is phi well defined? So when you are dealing with, if a point has different representatives, then we are bound to show that our map is well defined, in the sense that if I choose any representative, the map doesn't depend on the representative I choose, right? Okay, so that means if L can be written as LW for some non-zero vector W, which is not equal to V, then I have to show that phi of LV is same as phi of LW. So the question is that so? Okay. So if L is LW, then what does that mean? We already saw that two vectors give rise to the same line if they are linearly dependent, or one is a scalar multiple of the other. So that means W is equal to lambda times V. So that means W is what? Lambda times ABC. So what will be, since ABC is same as lambda A, lambda B, lambda C, according to our algebraic definition, we get that phi of LV is same as phi of LW. Are we clear? Yeah. Okay. And conversely, okay, now we have defined a map from the geometric definition to the algebraic definition. We sent a line to a point. Now we'll take a point and send it to a line. So conversely, take a point P in P2 denoted by X, Y, Z. And so now let W be the vector in R3 whose coordinates are X, Y, Z. Then now we are sending this point P to the line generated by W. Okay. Now again, we have to say that this map is well defined, right? Because this point also has another representative. That is, if P can be written as X1, Y1, Z1, then if we take another vector V, whose coordinates are X1, Y1, Z1, right? Then, so P can be written as X1, Y1, Z1 means X1, Y1, Z1 is nothing but lambda times X, Y, Z. So V is nothing but lambda W for some lambda in R star. So therefore, LV is same as LW. So again, our maps are well defined. So once we have this map in mind, I think now it's easy to say, see that the compositions, phi composition C and C composition phi give the identity map, right? Because you start from a line LV, and then you go to, if V is ABC, then you go to A colon, B colon, C. And if you have A colon, B colon, C, you go to the line LV. And yeah, so now it must be easy to see that both the maps, the compositions are identity, and therefore the sets are in bijection. Okay. So now we have seen an algebraic definition, we have seen a geometric definition, but still, can you see it as an object? Is it some object which we know already, right? So in the next section, we'll try to address this. So projective plane, how to visualize. Before we see some pictures, let's understand the set P2. Okay. In the set composition of P2. Okay. So I'm going to decompose this set, and I really wanted to put pauses, but then there is some issue in putting pause. So it's don't look at it together at once. Just read it with me. So P2 is this set X, Y, Z such that X, Y, Z is not equal to 0, 0, 0. I can decompose it into two parts where I'm writing it as a union of two parts. The first part is Z is non-zero, and the second part is Z is 0. Okay. So that is the second line. So we are decomposing it into X, Y, Z such that Z non-zero, union X, Y, Z such that Z is 0. So if Z is non-zero, we know that X, Y, Z is same as lambda X, lambda Y, lambda Z. And since Z is non-zero, we can divide the first two coordinates by Z, and we'll get 1 in the third coordinate, right? So this set can be written as X. So this, you can think of it as X1, Y1, 1, because this in fact is X by Z, Y by Z, 1. but since X and Y are like arbitrary and I'm letting it vary over R2, I'll stick to XY, okay? Okay, so this part, X, Y, Z, Z not equal to 0 can be written as X, Y, 1. And now we have the other part where Z is 0. If the third coordinate is 0, since all the three coordinates cannot be 0, we still have this condition, okay, where X, Y is non-zero. Okay, so now we have this piece of data. Keep it with you. Now we'll decompose this, okay? Now, here again, we can decompose it into two parts where Y is non-zero and Y is 0. And so if Y is non-zero, again, since X, Y, Z is equivalent to lambda X, lambda Y, lambda Z, I can divide my second coordinate by Y, and since Y is non-zero, and I'll get 1 in the second coordinate, 0 in the third coordinate, and X I'm letting it vary over R. Okay, and this remains as such. So Z is already 0, Y is 0, so X cannot be 0. And since X is non-zero, I can divide, because X 0, 0 will be same as 1, 0, 0, right? Okay, so I have this point 1, 0, 0 here. I have X 1, 0 here. So X is varying over R. So you have R many points here, and here XY is free to vary over R2, and you have R2 many points here. So what we are seeing is I have decomposed this projective plane into union of three parts. One is R2, the second part is R, and then there is a point which I am calling it infinity. You can call it whatever you want, but the convention is to call it infinity. Okay. I think, should I spend some more time on it? Do I need to explain it anymore? I think I need to hear an yes or no. Was it clear, or should I explain it once again? Anybody from the audience?
Clear, ma'am.
Okay. Do the others agree?
Yes, ma'am.
Okay, perfect. Yeah, so what have we, I'll just summarize again for my own satisfaction. So what we have is the coordinates x, y, z, and we have decomposed. We have this condition that x, y, z is not equal to 0, 0, 0. And we also know that x, y, z is same as lambda x, lambda y, lambda z. Using these two facts, we have decomposed this set into three parts. The first part is R2, the second part is R, and the third part is infinity. Okay, now we'll go and see some pictures. Right. So this tells us that our ordinary plane is R2, right? It is sitting in this projective plane. Okay. Yeah. Now consider the usual three-dimensional space with coordinates x, y, z. Okay. Yeah, so I think you can see it here. You have x, y, and z, and there is this plane that is the z equal to 1 plane, and that means the points in this plane would look like x, y, 1. Okay, and you can see a dotted line passing through the origin and intersecting the plane at a, b1. Right. So yeah, for each point in the z equal to 1 plane, there is exactly one line passing through the origin and the given point. Yeah, you take a point here and then draw a line through origin. So what I'm going to say is that for every point in the plane, we have a line through the origin. Similarly, like we saw that R2 is sitting inside P2, right? So this is like your R2. So, and P2 is all lines passing through origin. So for every point, you have a line passing through the origin. But then does it cover all? So what we have done is we have identified the points on the z equal to 1 plane with points of P2. That is lines through origin. But then note that there are other lines in R3 which passes through the origin and does not intersect the z equal to 1 plane. Okay, what we have done is we have taken a plane in R3, and we have put it inside P2 by taking lines through each and every point of the plane. But then that is not whole of P2, and that is not because there are more lines in R3 which does not intersect z equal to 1, or yeah. And can you think of an example? You can clearly see that, right? The x-axis and or the y-axis does not intersect z equal to plane, and all lines which are lying in the xy plane and passing through the origin, they also do not intersect the z equal to 1 plane. Yes. So these lines, okay, these lines we are calling it points at infinity in the projective plane. Okay. So we have a plane R2, which is the z equal to 1 plane, and we have a lot of lines which does not lie in the z equal to 1 plane, and those points we are calling points at infinity in the projective plane. Let us quickly go back to our set description. Yes. So here you can see that we have R2, then you have R union infinity, right? So this R union infinity will be called the line at infinity, and the points in R union infinity will be called the points at infinity. And this xy1, this R2 is the z equal to 1 plane. I hope I've given a better visualization of P2. So that means you have R3, there is a plane at z equal to 1, and then there are a lot of lines, and yeah, which does not lie in z equal to 1. And I have another way of visualizing the projective plane. Okay, wait, we did this, right? Yeah. These lines are called points at infinity in the projective plane. And next we'll see another visualization, and where I'll try to illustrate this parallel lines intersecting at infinity concept. Okay. Projective plane and the sphere. Yeah, so I'm not saying that projective plane is the sphere, okay? There is a projective plane can be seen as a part of the sphere. That's all I'm saying here. Okay, so the mantra is this. We have to find one point for each line passing through the origin. It doesn't matter if we find that point in a plane or on a sphere. So that's what we are going to do. So yeah, look at the sphere. Yes, you can see the 3 axes, you can see the origin, and now try to imagine lines passing through origin. Okay, you can see that these lines will intersect, yeah, the upper hemisphere and lower hemisphere, right? And let's forget about the upper hemisphere because we just need one point for each line. So let's focus on the upper hemisphere. Okay. You see that they intersect the sphere at exactly 2 points, one above and one below. Consider only the intersections of these lines with the upper hemisphere. So yeah, so this upper hemisphere describes all the lines passing through the origin except for the ones which is lying flat on the xy plane. Do you understand? So like forget about the lines which are lying in the xy plane, but everything else is every other line has a point in the upper hemisphere, right? Or if I take a point in the upper hemisphere and if I see the origin, that line through it, we get a line through them. And if I have a line, which is not lying in xy plane passing through the origin, then I get a point on the upper hemisphere. So now we'll see. So what happens to the lines in xy plane? So they also intersect the equator, right? Equator is that light green, dark green circle. Yeah, you understand equator, I guess. Yes. Yeah. So let's look at lines lying on the xy plane. So they intersect the equator at 2 points. We just need 1 point. So let's forget about the left green circle. I mean the lighter green circle. Let's focus on the darker green circle. So for the lines which intersect the equator of the sphere at 2 points, consider the dark green semicircle. And now what is left is our x-axis. So that's here. So for that, you consider the dark red point. For the x-axis, choose the dark red point. Okay. So like before, we had the z equal to 1 plane, and then we had lines lying on the x-axis, I mean xy plane. Yes, and the z equal to 1 plane is covered by the upper hemisphere, because all lines which are outside the xy plane, and not completely outside, I mean which does not completely lie in the xy plane, touches the upper hemisphere in one point, and which completely lie in the xy plane, for that we have points on the equator, and we are taking the dark green semicircle, and for the x-axis we are taking this point. Okay, so now you can see the projective plane in a much better way, right? It is like the union of the upper hemisphere, the dark green semicircle, and this point, this red point, dark red point. Okay, so we'll try to relate both the visualization. See, we can see that lines through the origin and a point in the upper hemisphere intersect the plane at exactly 1 point, right? And if I take a point in the plane, and if I draw a line through the origin, it will intersect the upper hemisphere at exactly 1 point. So so what I'm trying to say is, this upper hemisphere and the visualization we saw before, that z equal to 1 plane, that this is how we are relating them. Okay, and the lines through origin that does not intersect the plane. So there are lines through origin which does not intersect the plane. So these are the points at infinity, and they correspond to the line that intersect the equator. Right. Okay, so we saw an algebraic definition, we saw a geometric definition, we saw 2 kinds of visualization. So my question is, do you see the projective plane now? Right? Yeah, so we saw a set description as well, right? We wrote it as R2 union R union infinity, and this R2, you can think of this upper hemisphere and take it out, stretch it out, it will look like a plane. So your upper hemisphere is giving you R2, and you think of this dark green semicircle, it is your real line R, right? And that point infinity, that is just a point which we are calling infinity. Yeah. Okay. So if now you know how a projective plane looks like, it can be written as R2 union R union infinity, or you can think of it as a part of a sphere which contains only the upper hemisphere, the half semicircle of the equator, and so I mean the line through the x-axis, intersect the equator at 2 points, and we just need only 1. That's all. Okay. Yeah. So now we'll see how parallel lines meet in projective plane, right? Okay. So consider 2 parallel lines lying on the xy plane. So how do you know that 2 lines are parallel? We compare the ratio of the coefficients of x and y, right? So we want a1 by a2 should be same as b1 by b2. So for example, take 3x plus 2y plus 5 and 6x plus 4y plus 9. So yeah, the ratios are same. Yes, and of course they do not intersect in the xy plane. So how do we transfer them to the projective plane? So like in the projective plane, we have 3 coordinates, right? X, Y, and Z. And remember, those coordinates were homogeneous coordinates. So what we do is we homogenize this equation. Yes. And at this point, let me recall that we identified the xy plane with the plane z equal to 1 in the projective plane. So to transfer the lines to P2, we add the set coordinate and homogenize this equation. So this is the non-homogeneous part, right? Like this 5. Like if it was 3x plus 2y equal to 0, then it is a homogeneous equation. But 3x plus 2y plus 5 is not a homogeneous equation. So the result is 3x plus 2y plus 5z is 0, and 6x plus 4y plus 9z is 0. Okay. So now note that when you substitute z equal to 1, you are getting back the original equation we started with. Like here, yes. Okay. So now we have transferred our parallel lines to the projective plane using these equations by homogenizing it. So now to compute the point of intersection, what do? We solve the system of linear equations, right? So when we solve it, what we get to see is put z equal to 0, and then we get y equal to minus 3 by 2x is a solution. Okay, so now let's write it as a point in P2. What does it correspond to in the projective plane? So it corresponds to the point 1, put x equal to 1, then you get y is minus 3 by 2 and z is 0. And we already saw that when z coordinate is 0, those points are called the points at infinities. So yeah, what we are getting as a solution to the system of linear equations is a point at infinity. So yeah, that is how, so I mean that the railway tracks intersecting at infinity is exactly the same as this. Yeah. I think that's all what I wanted to say regarding projective spaces and parallel lines meeting at infinity. So I will, yeah. So I mean, yeah, I started with projective plane, right? But then there is a simplest projective space called the projective line, and I'll quickly define them, right? P1 is the simplest projective space, and like you would guess, the geometric definition is set of all lines in R2 passing through the origin. Because for projective plane, we took all lines in R3, and for projective line, we are taking all lines in R2. And yeah. And the algebraic definition, as you would guess, is again, we have only two coordinates. Again, homogeneous coordinates, x, y in R2 such that x comma y is not equal to 0, comma 0. So here again, you would take R2 minus 0 and then give the same, define the same equivalence relation and then consider equivalence classes. And this is how it looks like. And as a set description, doing what we did, like imitating our previous method, we get it as R union infinity. As a homework, you all could try to visualize how P1 would look like. These are the references. Most of the talk was from this blog and some pictures from here. And yeah, that's all. Thank you for your attention. I would like to take some questions now, if you have. I am done.
Thank you, ma'am. Thank you for such a valuable session. Now I will invite Ms. Ravina Ratnakaran of Second PG Mathematics, Sacred Heart College for Women, to deliver the vote of thanks.
Oh, before that, like, can you ask the audience if they have any questions or like?
Sure, Arusha ma'am. If the participants have any doubts or clarifications, please do ask. You can unmute and ask, or you can type in the chat box. Ma'am, Siddhartha Roy has asked whether you can suggest any book regarding the subject.
Yeah, so these projective spaces are usually taught as a part of something, either from quotient topology or algebraic geometry. So as such, I think you can Google introduction to projective spaces and read whatever is available, or look through one of the references. Because yeah, there is no book where it would be written like this, because the point of a book would be higher than just explaining what a projective plane is. I think I would suggest to look at this blog. Yeah.
And Siddhartha has again asked, is it a part of complex analysis?
Yes. Most definitely, yes. I mean, I think elaborating further on that or how it is related to complex analysis might be a bit too much. Or yeah, for projecting, we define an objective function because every point on x-axis is because every point on axis is projected to a single point. Define a projective function. I think.
Vishwajit, can you unmute and ask what's your idea?
मैम हम दोनों को अगर रिलेट कर रहे हैं मैम आर क्यूब को आर मतलब एक प्लेन से, तो वहाँ पे हम लोगों ने बताया कि मैम
प्लेन से रिलेट करना है,
प्रोजेक्ट कर रहे हैं ना मैम हम लोग को, मतलब पूरा आर क्यूब को प्रोजेक्ट कर रहे हैं ना। सो आपने बताया मैम पूरा एक्सिस पे जो भी पॉइंट्स होंगे उनको हम स्फीयर का, जब आपने बताया तो एक पॉइंट पर हम लोग कंसंट्रेट कर रहे हैं। तो सारे पॉइंट्स को हम लोग उस पॉइंट पर कंसंट्रेट कर रहे हैं ना जो एक्स एक्सिस के पॉइंट्स होंगे। तो एक्चुअली एक बाइजेक्शन से ही हम लोग कर रहे हैं ना। सो अगर हम लोग मतलब उल्टा अगर देखेंगे तो फिर वो बाइजेक्शन नहीं होगा ना।
किसको उल्टा देखना है? वो हेमिस्फीयर और उस
मीन्स अगर उस पॉइंट से हम लोग को पता करना हो कि उस आर क्यूब में किस पॉइंट को हम लोग उस पर मैप कराए हैं या प्रोजेक्ट कराए हैं, तो पता नहीं कर सकते ना। एक्स एक्सिस को ही उस पर।
मुझे एक्चुअली तुम्हारा क्वेश्चन समझ नहीं आया है अभी भी। लाइक I can explain what I said. What we did was, for every line passing through the origin in R3, we found a point on the sphere. And I didn't say that the whole sphere is same as the projective plane. We took only a part of the sphere. And so if I define a inverse map from that part of the sphere, the upper hemisphere, that semicircle and one point, then we'll get a bijection. We are not trying to do it from the whole of sphere. So, someone's muted. Did I answer your question? I hope so.
Yes. No, non-यूक्लिडियन ज्योमेट्री के बारे में कुछ अच्छा बुक बताइए ना।
किस चीज के बारे में?
यूक्लिडियन ज्योमेट्री, एडवांस लेवल।
Oh, I don't think I mean, I right now I don't remember any books as such to suggest you. Oh, I'm clueless. I didn't hope for a question like this. Yeah, I'm sorry. You can, I think Google is the best place. Yeah. Euclidean geometry, advanced level.
Ma'am, there's one more question about, I think he's asking about MTTS.
अच्छा, MTTS के बारे में आप कुछ बता रहे थे starting में, because I joined late. So I hope you all know about MTTS programs which happen like every year. It gives what I probably was saying was I have attended all 3 levels of MTTS and I learned how to do math from MTTS. Yeah. Congratulations. Yeah. Okay, I think we can stop if there are no further.
Yes, ma'am.
Yeah,
yes, ma'am.
yeah,
We can. I
yeah.
think we can wind up.
Yeah.
So we'll move to the conclusion. Christina, can you conclude?
So thank you for giving me this opportunity. Yeah.
Okay, thank you, ma'am. I invite Ms. Ravina to deliver the vote of thanks.
Good evening to all. On the behalf of Sacred Heart College, I am here to offer vote of thanks for the National Enrichment Program. I extend heartfelt thanks to our chief guest, Dr. Arusha ma'am, for joining with us and for giving a wonderful section on a candid introduction to projective spaces. I'm definitely sure that it was very helpful to us. Thank you, ma'am, for spending your valuable time with us. I'm also utilizing this opportunity to express my gratitude to the organizers of the section. My deep sense of appreciation to all the participants. Once again, I thank you everyone for joining with us in this evening. Thank you.
Thank you, Ravina. The link for quiz and feedback form will be shared in the chat box. Thank you, Arusha ma'am, and thank you all for joining us today.
Thanks, everyone.
So on behalf of every organizer behind this program, Arusha ma'am, thank you so much.
Thank you, Smita. Hi. Maybe we can stop the recording then. Yeah.
Yes.
Yeah.
Lynette,